So arguably, for our purposes, the most important use of the dot product is as a way to calculate angle measure. Now, obviously, the dot product doesn't just give you an angle because we got some crazy numbers back there, but the dot product itself is part of a formula that will give you the angle between two vectors. So that formula is as follows. Cosine theta equals u dot v divided by the magnitude of u times the magnitude of v. And what you need to make sure you know about this is that u and v must have the same initial point. Must have the same initial point. Okay, so u and v have to have the same initial point. And you're probably thinking, Mrs. Weber, it says that right here. I know it does, but it's worth writing twice because you're going to forget sometimes. Now, if you're just given vector u in component form and vector v in component form, you can assume that you have placed them with the same initial point. But if you aren't handed vector components and you're given points in space and you're making vectors out of the points, if you want to find like the angle at point A, you have to be doing vector AB and vector AC. You can't do vector AB and CA because if you do, you're going to have the negation of what you want, which is going to give you the supplement of what you want, because the cosine function has different values in the first and second quadrant. Inverse cosine of a half is 60. Inverse cosine of negative a half is 120. Okay, so long story short, make sure they have the same initial point. Okay, got it. Now, what the heck do dot products have to do with trig? How would I get a cosine formula out of just multiplying and adding? That seems weird. Here's how it happens. The law of cosines. And what's that, you say? Remember the law of cosines? It was a while ago, and you had that formula that was c squared equals a squared plus b squared minus 2bc. Nope. 2ab cosine c. And if you're thinking, no, I do not remember, that's okay. I'll remind you. What it says is if you have any triangle, right triangle or otherwise, and you want to find the length of a side or one of the angles, you can use this formula. And it says if you use the angle C, then put the side across from it alone. The side across from a given angle can be found using this formula. It's really technically an extended Pythagorean theorem, because notice how you start with Pythagorean theorem, c squared equals a squared plus b squared, but then you take away a little bit if it's an acute or an obtuse. So if it's an acute angle, you would take away a little bit. If it's an obtuse angle, you'd add a little bit of it. Think about why that works. So anyways, there's the law of cosines. We're going to use the law of cosines to create a formula for cosine C. So I'm going to solve for cosine C here. And if I do that, I'm going to end up with cosine C equals, let's see, I could add this, move that. So it'd be a squared plus b squared minus c squared divided by 2ab. Okay. What does that have to do with dot products? I will show you. So in this formula, the big capital C is the angle that we are interested in. In our diagram, that's theta. Cool. A is one of the adjacent sides to the angle you're talking about. Well, one of these adjacent sides is u, but technically u is a vector. I want the length of the adjacent side, so I really want to use the magnitude of vector u. So A is vector u. B is the length of vector v. C is the length of the vector across from the angle, which is v minus u. And again, A and B are the lengths of the adjacent sides. Okay, I'm getting closer. The formula that we are attempting to mimic and replicate is cos theta equals u dot v over the magnitude of u times the magnitude of v. I mean, I've got that on the bottom. I just need to kind of get rid of that 2. And, oh, yeah, that doesn't look like a dot product on top. So if I want to figure out the dot product on top, geez, I don't see it. So what we're going to do is break this down into its components. And we're going to say cosine theta equals. The magnitude of u squared would really just be the sum of the squares of u's components. okay? Now, we can do this in 2D or 3D. I'm going to do it in 2D just so you don't have as much to write, but trust me, it works in 3D just as well. So if I say vector u has components u1 and u2, and vector v has components v1 and v2, then the magnitude of u squared is going to be u1 squared plus u2 squared, v1 squared plus v2 squared. And then, okay, so v minus u is up here. And when I subtract vectors, I just subtract their components. So this would be v1 minus u1, v2 minus u2. And so if I do that, those magnitudes squared would be v1 minus u1 squared plus v2 minus u2 squared. But I'm supposed to subtract that whole vector, so I'm just going to distribute the minus sign over to here. Some of you are screaming, Mrs. Vibber, you just made it worse. Yes, I did. I set the dumpster on fire so I can get it to a previously solved solution or previously understood solution. Okay, this still looks a lot worse, but you know what? When I square a binomial, I get a trinomial. So I'm going to pull these trinomials out. So I have cosine theta equals yada, 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 and then minus v1 squared minus u1 squared, then it would be plus 2u1 v1, and then minus v2 squared minus u2 squared plus 2u2 v2. And that squiggle used to be u1 squared plus u2 squared plus v1 squared plus v2 squared. And if there's one thing that we can all agree on in mathematics that we really enjoy doing, it's canceling crap out. We get to do that now. Yay! So u1 squared minus u1 squared, u2 squared minus u2 squared, v1 squared minus v1 squared, v2 squared minus, there it is, v2 squared. So all of those subtract to 0. And then I got a bunch of 2's on top. So this 2 would divide with those two 2's. And so now what I've got left is cos theta equals u1 v1 plus u2 v2 divided by the magnitude of u times the magnitude of v, u1 v1 plus u2 v2. That's the dot product. Da, 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 da. So now I have the proof for that cosine formula. And if you're thinking, dear God, Mrs. Vibber, why do we go through all that? Can't I just use the formula? Yes, you can. However, I want you to understand where it came from. It didn't come out of thin air. You can get it. This also kind of emphasizes the need for somebody at some point in mathematical history to define the dot product, because there were many formulas where they would go through and do this stuff, do this geometry with the vector components and realize, wait, this is first component times first component plus second component times second component. That kind of operation happened enough that they just said, okay, instead of using that every time, let's just call it the dot product to make our lives a little bit easier. Okay. Now let's do some angle stuff. All right. So we are going to calculate some angles over here, and, then we'll be good to go. So it says U, V, W, Z, find the angle for each pair of vectors. So what's important here is I'm handing you vectors in component form, so you can assume that these vectors all have the same initial point, okay? I know there's the whole thing about assuming. It's okay. If vectors are given to you in component form, they are translatable. You can stick them with the same initial point. So if I want the angle between U and V, cos theta is going to be U dot V over the magnitude of U times the magnitude of V. So cosine theta is going to be U dot V. So 3 times negative 4 is negative 12, plus 1 times 0, 0, plus negative 2 times positive 2, negative 4, divided by the magnitude of U, so that's the square root of 3 squared plus 1 squared plus 2 squared, that's 14. And the magnitude of v is the square root of 4 squared plus 0 squared plus 2 squared, which is the square root of 20. So I have cos theta equals negative 16 over the square root of 14 times 20 is 280. And so then in my calculator, I am going to do the inverse cosine of negative 16 over the square root of 280 eventually. So my face is in the way. Inverse cosine negative 16 divided by, whoop, shouldn't have entered that parenthesis. Divided by the square root of 280. 2.8. Oh, nope, I defaulted back to radians. I don't want to be in radians. I want to be in degrees. (162.97). So we're going to say that's 163 degrees. Theta equals 163 degrees. Cool. All right, I want you to find the other 3 angles because I'm pretty sure you can do that on your own. And so pause the video. I'm going to pause my video, and then when you come back, they will all be there, hypothetically. How do I pause my video? Up here. And we're back. And I used fun Greek letters for my angles. You don't have to do that. But for part B, I called my angle alpha. Got 33 degrees. For part C, I called my angle beta and got 90 degrees. And for part D, I called my angle phi and got 180 degrees. And so wait a second, what happened to part C? What happened to part D? Why did it happen? What does it mean? So what it means here is when we had a dot product that went to 0, that means cosine theta equals 0. And the only time that happens is when your angle is 90 degrees. That's a big deal. You need to make sure you know that. If the dot product equals 0, then the 2 vectors are perpendicular. And in this class, sometimes we will call that orthogonal. Because believe it or not, there are kind of different kinds of perpendicularity. So perpendicular or orthogonal, you can use either word, that's fine. And then in part D, we got 180 degrees. So if you think about it, if I have 2 vectors that are 180 degrees apart, they look like that. They're also parallel. So if you have 2 vectors that are parallel, you will either get an angle of 180 or you will get an angle of 0 because your cosine will equal 1 or negative 1. So whenever your vectors are parallel, you will have an angle of either 0 or 180 depending on if they point in the same direction or opposite directions. All right, and the last thing, example, points A, B, and C, create a triangle in space, find the measures of the 3 angles of the triangle, and then classify it. So for this one, same thing. I don't want to make a whole video of me writing this stuff down. So why don't you give that a shot, pause this, and then come back. Okay, so I finished up with the angles, but one thing I want to make sure you all understand is what I said before is true. You have to make sure they have the same initial point. So when I want angle A, I had to find vector AB and vector AC. And then if I wanted angle B, I needed to find vector BA and BC. So if you did all your work and you did it just based on the points, nope, you got to go back and fix it. You have to find angles based on vectors. And if you did all your work and you did it based on vectors but forgot to give them the same initial point, you might have had a problem where these 3 angles did not add up to 180 because 1 or 2 of them are likely the supplement of what you were supposed to get. All right, so that is the end of that video. Joke for the day. This is another one of my kids' favorites, just to remind you, what color is a burp? What color is a burp? Purple. That's it. I got Mr. Marriott to laugh. It counts. Have a good day, guys.